have Marissa Baskett. Dr. Baskett is one of our own. She's here in the Department of Environmental Science and Policy. Her research focuses on theoretical ecology applied to conservation biology, using mathematical models to investigate under what conditions anthropogenic impacts and global change can cause rapid evolution and community shifts, with a focus on marine systems. Today, she will talk to us about considerations for modeling the dynamics of small populations. Dr. Baskett.
Thank you, and also thank you very much for the invitation to come to speak with this group. This is a very exciting symposium. And when one thinks about the topic I was asked to speak about, population dynamics, in the context of our topic for today, conservation of species on the brink of extinction, as the organizers have put it, usually the first thing that comes to mind is population by birth. Whether that is constructing it on your own or using some sort of pre-packaged software program like RAMIS. From that, constructing analyses of, say, cumulative probability of extinction over time or minimum viable population, and using that to inform our management of these populations. And of course, PVA has its promoters and its detractors, and the sense of when is it and is it not useful. And rather than wade into that debate, I would like to take a step back and point out that all PVA is, at its heart, is constructing a model to assess extinction risk. And so we can look at our basic modeling philosophy, even going to somebody who developed models for another discipline, that everything should be made as simple as possible, but no simpler. We should construct the simplest possible model to achieve our goals, because that gives us the tractability to understanding what drives what in our model outcome, but also as simple as possible, but no simpler, that we do need to include everything that's most important. And how do we decide what's most important? Well, that depends entirely on our question. So we focus on the question we're asking and construct the simplest possible model to address that question. And our goal here is understanding extinction risk, and in particular, what are the management actions most likely to reduce that risk? So I'm going to spend the bulk of my time talking about what dynamics we might throw into a model that looks at this goal of assessing and managing extinction risk, but also spend a little bit of time at the end talking about analyzing and applying these models and also some future challenges. And there are a lot of dynamics we could possibly consider. I'm going to give a bit of a whirlwind tour, but the question I'm going to ask is then, how do we avoid throwing everything in the kitchen sink too? How do we decide when and when not to put in some of these dynamics? So, starting off with stochasticity. When we think about, there are two major, stochasticity is often divided into two major categories. Demographic stochasticity is this individual by individual variation in survivorship and reproduction. And so, say on average, a population, every individual might have 2.3 individuals. Well, some have 2 and some have 3 and so on. And a catastrophic outcome or an extreme outcome, like somebody having no offspring, is going to, on average, affect a smaller population more than a larger population. So we tend to think of demographic stochasticity when we're thinking of small populations. This is very typically something we'll consider. Environmental stochasticity, this tie of the population dynamics to some sort of environmental condition, on the other hand, is going to be much more important for species with shorter life histories. Just showing a quick example of variable rainfall in time, and you can see that your annual plants are going to be quite variable in this variable environment, whereas a perennial plant, even though its seed production might be variable, will be able to average it out through this longer life history strategy. So that constrains when we think environmental stochasticity might be most important. But these aren't the only types of stochasticity we might consider. Here's a study by a couple. Davis, Brett was at Davis when they did this study, when he did this study with Alan. And what they did is look at, first, putting in demographic stochasticity into a model, looking at extinction risk in terms of time to extinction as it depended on a central model parameter, the rate of increase in the model. And so you got in a sense of extinction risk from that demographic stochasticity. Put an environmental stochasticity on top of it, you get some more enhanced extinction risk. Your time to extinction goes down. But if instead of including environmental stochasticity, you include what they called a stochastic sex ratio, that some individual, just like births and deaths are a coin flip, that happens with a certain probability, so as having male and female offspring, that actually reduces or increases your extinction risk by quite a bit more. This is a log axis on the y-axis here. So we're talking orders and orders of magnitude here. And similarly, what they call demographic heterogeneity, that in addition to each individual having a coin flip for how many offspring or whether they'll survive, it's also each individual might inherently have a different potential fecundity or survivorship. That similarly has a much greater effect for this particular model on extinction risk than our environmental stochasticity. So these types of simple models can give us guidelines into which types of stochasticity might be most critical to determine. Another type of stochasticity often discussed, and that we heard about this a bit this morning, is the idea of genetic stochasticity. One of the long-standing debates is whether or not genetic stochasticity and its effect on loss of genetic diversity and potential for inbreeding depression gets outweighed by demographic considerations. And there are a lot of cases where this is true. There are certainly some great exceptions to that, like we heard about this morning. In particular, the idea where we can tie it to some sort of management action, and whether or not that management action is helpful, like genetic rescue, then it would be something important to put into your model to understand the prioritization of that. So for some species, this might be a consideration, but traditionally conservation genetics has been focused on the question of diversity for diversity's sake. There's a bit newer and overlapping field of evolutionary conservation biology, which is a more trait-based approach, and interested in this question of biases and human impacts, actually incurring selection on particular traits, and those traits affect the viability of the population. And we have a long-standing example of this being important in small populations when we go into captive breeding. That it's sometimes very difficult to avoid domestication selection in captive breeding, and that can select for traits that very much reduce the viability of the population in terms of effects on things like reproductive success. And here's an example from salmon, and this is salmon hatcheries, and this is something in my own work I've been getting interested in quite a bit recently. And one thing we found, just to give a sense of, again, what models can provide in the sense of this, is that if we look at on the x-axis, as we move to the left on it, we're getting stronger and stronger selection in captivity, and we're looking at what happens in terms of its effect on the wild population when they interbreed. And all these different lines, the details aren't important, but the idea is all these different lines represent different life histories in terms of when your salmon are released relative to density dependence and when mating occurs. And that really drives what effect this selection in captivity has. So understanding your life cycle can be quite important when you're worried about domestication selection. And also, normally we don't consider density dependence for small populations, but this might be a particular case where it's important to consider. Of course, a lot of traditional population viability analyses look at age and stage structure, in part because age and stage are one of the major sources of that demographic heterogeneity that the Melbourne and Hastings paper showed could be quite important. And also because in some cases we can apply, our management might affect different ages or stages differently. The classic example here being the sea turtle example that we all the Davisites heard Larry Crowder present earlier this year, that we can look at in terms of which management action has the biggest effect on the outcome. Actions that, say, restore beaches and protect the eggs and hatchlings of our sea turtles versus actions that protect subadults and juveniles, like putting in turtle excluder devices. From breaking down this population into this stage structure, we can get a sense of which management action is going to be most likely to reduce our extinction rates. So that gets the idea of building our model to tie it to the question of management actions. Spatial management is again something that often quite comes up, in particular for species where spatial dynamics are a really major part of their life history. And on top of this, again, in terms of tying it to our management decisions, where the human effects that are determining the extinction risk for this species are also spatial, like our spotted owl, where habitat fragmentation can affect its potential for the juveniles as they disperse to find new nesting sites different from their parents. And another very classic population viability analysis example. Of course, small populations, we often fall back to the question of allele effects, whether or not there's a threshold population size necessary for growth, and you have positive density dependence driving that. And usually when we think of allele effects, we think of reliance on aggregations for breeding, like these abalones that might be mass spawning, and difficulty in finding mates when we get small populations. But we have to remember that that's not the only thing that can drive an allele effect. In general, species that rely on aggregations for all sorts of activities, predator evasion, foraging, resource acquisition, say plants needing higher densities to be able to trap nutrients and water with their roots, all of those can drive allele effects, and so any sort of aggregation requirement would mean a species where you would want to incorporate that into your model. And species interactions are another thing that can drive threshold effects, just like allele effects. So normally you're thinking about your small population, other species that might interact with it that have much larger populations, you could probably assume are relatively constant. That's one of the simplifying assumptions you can make from your model. But there are exceptions to this, like with everything else. If you have strongly interacting species, say a specialist predator, where you have a strong dynamical feedback, you have disease dynamics, might be another example. And if again, your species interactions can fall back to your management choices, like with invasive species. And one case that comes up quite a bit is when species interactions lead to threshold effects that can look quite a bit like allele effects. So one that's come up quite a bit in the fisheries literature is the idea of what's called cultivation effects. That your large-bodied species, which are typically the species we fish, like our yellow-eye rockfish here, this species declined so much that there was for several years a major fisheries closure in order to protect it and a couple other rockfish species that have declined quite a bit. These large-bodied species, their prey might either compete with or eat their own juveniles. So if the population size down of the large-bodied species, the prey have a lot less predation going on, they explode, they can inhibit the growth of the juveniles and therefore the recovery of this species. So a really simple model looking into these types of cultivation effects can tell us a couple things. For example, first of all, generally, how big of, say, an area do you need to set aside in order to start to see recovery of your large-bodied species? But also give a sense of where this threshold is necessary for the growth of the growth of the larger-bodied species. And that threshold could also be in terms of the interacting species as well. And so some have proposed, based on these types of models, translocating organisms to get to high enough densities such that you expect growth, or even more controversially, culling the species that might be inhibiting that growth. So that is our whirlwind tour of things we might want to throw into these models. In terms of how we analyze them, there is another long-standing debate over how much we can truly assess extinction risk and how accurate that is. And that's another debate I'm not going to quite wade into because a number of people, including these authors, have really well-established things like, well, how does the question of our ability to assess extinction risk depend on the types of stochasticity and how much stochasticity we see in the population we're modeling. I would say, though, the more important application is this question of what are the management actions most likely to reduce that risk, right? That's our actionable information we get out of these models. And the classic way to do that is sensitivity analysis, to say, well, for every unit change in my variable in PVAs, it's usually that growth factor. right? But it doesn't have to be. It can be population size. If you have a stochastic model, average population size over time. Maybe you care more about variability. How Caswell is really developed, how do we look at these sensitivity analyses? So the proportion change in your variable for proportion change in a parameter. Maybe you want to do elasticity, normalize it, and so then you might tie those parameters to management actions, your survivorship in your hatchling stage versus your subadult stage, for our sea turtle example. And that can then help inform management. But that's not the only thing we can look at sensitivity to in a model. We can also look at sensitivity to relaxing certain model assumptions. And that also tells you what's most important to the model outcome. Does it substantially change the dynamics? This is what theoretical ecologists have been doing since the get-go. And so both of these can inform which management choices have the largest effect on the outcome. And just to show a quick example, again, I'm using some of my own work here, not because they're the best examples, but because they are the examples I know best. When a theoretician presents results, they should know the fundamental assumptions behind the model they're presenting. So this is an example from a coral reef model, where we looked at the potential for corals to genetically adapt to the future temperatures we expect with climate change, given the potential impact of climate change in terms of coral bleaching. And we did sensitivity analysis to all of the parameter values we put into these models. I'll get back to that later. But we also relaxed some model assumptions. Like, say, what if we had two locations that had different stress levels and ran the model with and without connectivity? Does that slow down the potential for a coral to be able to adapt to local conditions? Or does it actually supply genetic diversity and demographic support to help it recover from an individual bleaching event? And we found actually that the rescue effect was greater than the slowing down of local adaptation. In terms of applications, we've of course been talking about the application of where to focus management efforts. But once you put those management actions into place, you are not done, right? You have to determine, were they successful? And that is generally the process of adaptive management. You have to monitor and evaluate. And when you're evaluating whether they're successful, you cannot do this without a model. That in terms of, say you get an increase in your population, was it as much of an increase as you expect? How soon can you measure to determine whether or not your management action was successful or not? You need a model to quantify this answer. And just a quick example from work by a bunch of Davis authors, while Will White was a postdoc here, on why models are important to adaptive management. This is a case of marine reserves. The shaded areas are reserves. The question of whether the classic comparison for the success of marine reserves is an inside-outside comparison. Are our population sizes greater inside compared to outside? Well, whether or not this serves as a good metric depends very strongly on the life history of the organism. For example, how much dispersal distance it has. And how soon you would be able to detect an effect depends quite a bit on how much fishing there is on this organism, both before reserve establishment and outside reserves. So finally, getting into some future challenges here. It's hard not to talk about future challenges in any field in ecology without bringing up climate change. To me, climate change, though, illustrates the general trend that's been happening for a long time now, that the impacts on these small populations are becoming increasingly global. So how do you think about local management and using models to inform local management under these global impacts? Adding another species that is threatened by climate change is not going to be what spurs the world into action to develop large-scale greenhouse gas mitigations. Climate change, though, also illustrates another major challenge into the future. And that's when you look at these types of climate models that predict temperatures into the future, you can see two major sources of uncertainty. The uncertainty in terms of what we're going to do, large-scale greenhouse gas mitigation or business as usual. There's also, of course, uncertainty into these model outputs. We, by no means, have the world's climate exactly resolved. And so when we plug these models into ecological models, which, of course, have their own sources of uncertainty, we get what Mark Schwartz called a propagation of uncertainty across all of these layers. And so how do we deal with these layers upon layers of uncertainty? So in terms of these global impacts, one thing models can tell us is about something that, again, we heard a little bit about this morning, the idea of protecting the capacity to respond to them. And that capacity can depend on local management. So pulling this coral reef example, one of the 7 parameters we found the model was most sensitive to are parameters related to the potential for macroalgae to grow after a bleaching event and then inhibit coral recruitment. And even though we're talking about a major global effect in terms of temperatures, locally this is something that can be managed in terms of protecting populations of herbivorous fish, protecting nutrient outflows that affect macroalgal growth. And also, in terms of our question of propagation of uncertainty, another thing these types of models, and in particular sensitivity analysis, can tell us is, do we have any unknown parameters that the model is particularly sensitive to? And that can help us resolve where do we really want to focus our future empirical work to help us at least reduce some of these uncertainties. And I know there are also a lot of new developing tools in terms of quantifying uncertainty, and that's something that the class talked about in terms of some exciting new Bayesian tools. So my end argument here is that, yes, we're facing some of these huge challenges in terms of propagation of uncertainty and global effects, but we can really build on the lessons we've learned from constructing these models for a long period of time in terms of how we build them, how we analyze them, and how we apply them in order to tackle these future challenges. Look at our basic modeling philosophy, even going to somebody who developed models for another discipline, that everything should be made as simple as possible, but no simpler. We should construct the simplest possible model to achieve our goals, because that gives us the tractability to understanding what drives what in our model outcome, but also as simple as possible, but no simpler, that we do need.
Today she will talk to us about considerations for modeling the dynamics of small populations. Dr. Baskin.
Thank you, and then also thank you very much for the invitation to come speak with this group. This is a very exciting symposium. And when one thinks about the topic I was asked to speak about, population dynamics, in the context of our topic for the day, conservation of species on the brink of extinction, as the organizers have put it, usually the first thing that comes to mind is population biology. Whether that is constructing it on your own or using some sort of pre-packaged software program like Ramis. From that, constructing analyses of, say, cumulative probability of extinction over time or minimum viable population, and using that to inform our management of these populations. And of course, PVA has its promoters and its detractors, and the sense of when is it and is it not useful. And rather than wade into that debate, I would like to take a step back and point out that all PVA is, at its heart, is constructing a model to assess extinction risk. And so we can
We have Marissa Baskett. Dr. Baskett is one of our own. She's here in the Department of Environmental Science and Policy. Her research focuses on theoretical ecology applied to conservation biology, using mathematical models to investigate under what conditions anthropogenic impacts and global change can cause rapid evolution and community shifts, with a focus on marine systems.